Hello, welcome to another exam review problem. So let's see how nasty we can get. Now let's do a second order system and let's go nuts with it. Let's give it an initial condition. We won't do a non-homogeneous second order just because. Well, actually no. Let's do it. Why not? We can do it. There's no reason we shouldn't. We haven't practiced this much, but we might as well swing a practice bat now. Let's make these problems as nasty as we can make them, just for the sake of practicing. I won't use coefficients, I won't use variable coefficients. I'll use numbers just to give some variety to how I do these. So I don't know, 4x double dot. At this point, somebody's got to be shouting 7, so there you go. There's a 7. Enjoy. And oh, I don't know. Somebody's going to be shouting 13 or some irritating prime number like that, but no, forget it. I'm not doing that. There. You give me a 7, I'm going to give a multiple of 7. Huh. Take that. All right. Small victories. Small victories. All right, and just to keep some symmetry in the system, I'm going to use this. So here we've got a forcing function. That's a ramp function. So we have a second order linear non-homogeneous. Just like we did with first order systems, I'm going to go ahead and split the solution into two parts. So x is going to be equal to the homogeneous part plus the particular part. The homogeneous part we can solve. We'll do that in a minute. The particular part, well, that's actually not too bad. So let's start there. That's actually the easier part, believe it or not. The particular part here is going to be a ramp function. We just need it to be some ramp function. At plus b, right? There. Now we've got to add this second coefficient to make sure we've got enough variability to fix it, right? So to make it fit. Let's go ahead and evaluate the derivatives. The big scary here is, wait a minute, this is a higher order system. How do I know this analysis is still going to work? Let's have some patience and let's see what happens. As it turns out, not so bad. This one makes it easy. So when I substitute this in to the particular solution, here's what we have. See, this really isn't so bad. Now I just need to find a and b so that this is true. This is now irrelevant. That's 0. And so if I just set like terms of t equal, we end up with this. 21a is equal to 21. Well, that's no mystery. Lovely. And then if I set the constant terms equal to, well, 0. Remember, there's a 0 here. So that means 7a plus 21b is equal to 0. Well, now you can see why I decided to make that 21 a multiple of 7. Let's see. So in other words, b is just negative 1/3. Okay. So we've got our particular solution. Lovely. That was actually pretty easy. It was just t minus 1/3. Okay. Now let's go about finding our homogeneous solution. This is the hard part, right? Remember? So 4x double dot plus 7x dot. So the homogeneous form of the problem is this. Is this. All right. So I've been remarkably uncareful in forming these coefficients. So what we don't know is whether or not we're going to get an overdamped or an underdamped solution. if we get underdamped solutions, these are the problems we've practiced, right? We haven't really looked at overdamped very much. So the underdamped cases, take this form. We end up with a solution that looks like this. And we might write a positive here. Yeah. You can write it either way. Phi is just an unknown. Usually, the reason to write a negative there is usually these systems are going to cause lag. So normally this is going to be a negative angle. But that's all right. We'll just solve for phi as negative. Now this is only if underdamped. All right, now I've been remarkably uncareful about solving for my coefficient, so let's find out if it's underdamped. Do you remember what underdamped is? That would be a good thing to review. All right, so step one, we've got to put this in canonical form. Is it in canonical form right now? Please scream no at your computer. No, it is not. The 4 prevents it from being in canonical form. We have to have a unity coefficient out here. The canonical form for a second order equation is this. This is worth knowing. So this is the canonical form. So we need to get this in that form. No problem. That's going to end up being xh double dot plus 7 over 4. Well, that's just 1.75. And this is 21 over 4, so that's 5.25. Let me write that just to make this a little easier. Okay, and now we set the like terms equal. So omega n, the natural frequency, is the square root of 5.25. Excellent. Let's see. Well, let me bring up my handy dandy Python terminal. Doo-doo-doo. I'm going to assume you don't need to see me calculate the square root of 5.25. I figure you can do that. All right, I get 2.29 thereabouts. 2.291 hertz, of course. No, it's not hertz. It's never hertz. It's radians. Radians per second. Radians per second. Do not write hertz. Do not write hertz. I will yell at your paper while grading it. All right, so that's omega n. Now we're ready to calculate zeta. So 2 zeta omega n is equal to the 1.75. Okay, so zeta is equal to 1.75 divided by 2 divided by 2.291, which is, as luck would have it, underdamped. I get 0.382, thereabouts. All right. All right, so remember, if zeta is less than 1, right, then it is underdamped, and that means the system does oscillate. You are going to get a ringing phenomenon in the system. So there is little enough damping that this system will oscillate, right? So we have its speed, right? This remember, omega n tells us about how fast the system is, and zeta tells us how strongly it will ring. There's a little bit of damping here. This is not I would call this a moderately damped system, right? It's in the middle. It's neither crazy high damping nor crazy low damping. So yeah, this is moderate damping. All right, so now we're ready to plug in. So we need to calculate. We've calculated omega n and zeta, but remember those don't actually appear in our homogeneous. Oops, you can't see that. Sorry. Those don't actually appear in our homogeneous response. These are the physical parameters that actually show up on that you can actually measure from an oscilloscope, right? So we have to convert these into these. No problem. We can do that. So damped natural frequency. That is the frequency you actually see on the scope. Is this. Okay. Let's go ahead and calculate that. Just a moment as I type this into my Python terminal. All right, and I get damped natural frequency of notice I'm carrying a lot of sig figs here. It's just a force of habit. I don't like to round. I like to truncate my sig figs at the end. All right, so yeah, there we go. So what you see is that the frequency is actually reduced a bit here. That's a little over That's over a 5% reduction, maybe about 7% reduction in frequency there, which is quite measurable from the natural. So of course, as damping goes up, you see the frequency is reduced more and more and more. Okay. Now we still need the time constant. Remember what the time constant means, right? The time constant is how long this ringing is going to take place, right? So how long does the ringing last? Okay, no problem. That's easy to calculate. 0.382 and times omega n. Don't use omega d here. Use omega n. 1.7. Oh, excuse me. Woo, wrong number. Sorry. 2.291. There we go. Handy dandy calculator. I get that to be about 1.143 seconds. So it's a pretty slow system, right? This is probably not, if this is an electrical system, it's a honkin' big one. It's slow. This is a slow system. All right, so we've got the parameters now. We are ready to assemble our total solution. So the solution as a function of time is all right, so that's my homogeneous solution. All I've done is plugged in for tau and omega d. And now I'm ready to combine my particular solution in with that. The particular solution was just this. All right. What did I forget to give us? Crud. I forgot to give us an initial condition. Oops. Let's say that the initial condition is 0. Great. What else do we need? Is that enough information? No, it's not enough information. For a second order system, you need 2 initial conditions, right? So let's say that there's some initial velocity. I don't know, 1. Why not? So let's say it's got some initial velocity. Okay, so let's evaluate this. We are going to use the 2 initial conditions as constraints that tell us A, and they are going to tell us phi. So those two, the phase and the amplitude of the homogeneous response. So the initial condition must equal to 0 when time is 0, is just a times cosine phi minus a third. Okay. X dot at time 0, which must equal to 1, we said. Well, this one's going to be a little more complicated, right? Okay, so I'll come back to this. First, let's evaluate x dot. Got ahead of myself, didn't I? So that's negative a over 143 cosine. Whoops. Ah! What am I doing? E to the negative. I'm going to be sloppy. Just pretend I wrote that out. All right. Plus sorry, that's also going to be minus you'll see why in a minute. All right, so what I've done is taken the derivative of this first term to get this, or the e, and that gives me this. Next, I take the derivative of the cosine. That gives me a negative sign, right? But then I have to multiply by the inside derivative of t, right? So that's where the 2.117 comes from. All right, and then finally, I just need to differentiate this stuff, which is plus 1. All right, not bad. Now, when I set all of this, when I set time equal to 0, right, the derivative of a third is 0, right? So this just has derivative 1. When I set all of this equal to 0, the e to this is just going to go to 1. This is going to go to cosine phi. This is going to go to sine phi. All right, let's see what we get. So a, what is that? Negative a over 1.143 cosine phi minus a times 2.117 times the sine of phi plus 1. All right, not bad. So there we go. We've got an expression for that constraint there. So now at this point we need to go through and start and figure out some way to solve for either phi or a. So in the past, we've been able to use some trickery here that usually works out, but these constants here are going to confound that. Now, I've got a pretty happy coincidence here that this 1 is going to cancel with my initial condition, and there's a good chance, well, in fact, I know I'm going to be able to use some trickery here. That wouldn't always happen. I'm never going to give you something on an exam that requires numerical solution, right, to back your way out. So anyways, like I said, this is as nasty a problem as I can come up with, but we can do this. All right, so why don't we start by trying to, we need a strategy to crack this open. Why don't we start by trying to eliminate, let's mess around with this equation here. I think this is the easiest one to get started with. So if I subtract 1 from both sides, right, I've got just this whole thing is equal to 0. And that leaves me with this. Okay, well, because this is all equal to 0, I get to divide by a, and I'm going to be okay. I got lucky, though. It didn't have to work out that nicely. So now I can solve for phi explicitly. If I just divide both sides by cosine, then I've got the tangent of phi is going to be equal to negative, what's that going to be? Yeah, there we go. That's solvable. Let me go ahead and figure out what that is. Well, Why do it in steps? Never mind, I'll just figure out the number. 1.143 times 2.117 is, all right, so the denominator is 2.42 about. So that this should be about 4, or 0.4 rather. Yeah, it's 0.413. Okay. So the arctangent of that all right, that's in radians. And if I, just for the sake of argument, put that in degrees, that's about 22.4 degrees. Okay, so we've got phi. Now we just need A. We can go back and solve for A. The easiest place is going to be right here, as a matter of fact. In fact, this is the only place we can get it from. So A is going to be equal to 1/3 cosine phi. That's just me solving for A here. So I'm just going to substitute my value so you can see what I'm doing. I got 0.924, again, crazy numbers of sig figs. Yeah, that's what I got for my cosine. And then my final answer for A, for the amplitude of this response, is 0.36. Again, let's get some extra sig figs in there just for safety. There we go, 3606. So, just to write it all in sum, what did we just learn? Our response as a function of time is, my goodness, what a lot of work, 0.3606 e to the negative t divided by 1.143 seconds. That has units. I'm being sloppy by not writing them. Cosine 2.117 t. That has units of radians per second. I'm being sloppy by not writing them. My phase lag here is 22.4 degrees. I'll put it in degrees just to make sure it's clear. Plus t minus a third. If I were to plot that, so the input, the input was doing this, right? So this was y. The quasi-steady response to the input here is lagging. The y-intercept is negative a third, so let's say that's about the y-intercept there. Okay, so this was my input, but this is the quasi-steady state response of x, so it's going to eventually relax into this. The initial condition for x, if I actually evaluate the derivative for this whole thing, it better evaluate to 1. So the derivative has got to evaluate to 1, because that was the initial condition. And at time 0, this should evaluate to be 0. So we should be able to show that. If that's the case, then the solution would look like this. It would start at 0 with an upward slope of 1, and would then oscillate about this response, like that. And so what you would see, if you looked at this on the scope, was some initial oscillation that decays away, right? So you'd see a decay envelope around that particular solution. And then you'd see, for the input y, you'd see the output lagging it because of this offset here. Okay, well that was fun. Thanks for watching.